This lecture covers the non-parametric test. Our main objective is to use the run test to determine whether a data set is random. Now, a run is a sequence of data having the same characteristic. Also, each run is preceded by and also followed by data with different characteristics or by no data at all. The number of data in a run is called the length of the run. Now, let's see an example. Here we have a liquid dispensing machine that has been designed to fill 1 liter bottles. A quality control inspector decides whether each bottle is filled to an acceptable level and passes inspection, P, or fails inspection, F. Determine the number of runs for the sequence and find the length of each run. So this is our sequence here. We have PP, 4F, P, another 3F, then P's. Now, based on the definition, it means our first run will be PP. So we have PP, then when it's F, we have 4F. So FFF, then P, then FF, then the rest is P. So this means we have 5 runs. So there are again 5 runs. And the length of each run will represent the number of P's or F's we have. So for the first run, we have 2 P's. Second run, we have 4 F's. Third run, 1 P. Fourth run, 3 F's. And the fifth run, we have 6 P's. Again, the concept here is based on the data given. So the sequence of PP, FFFF, P, FFF, and 6 P's is what is given to us. So here we're able to find how many runs we have on the data set and also the length of each run. Now, next we are going to do the hypothesis testing. So run test for randomness. So our goal of this lectures is how to perform a run test for the randomness. So here we say a non-parametric test that can be used to determine whether a sequence of a sample data is random. For example, as the previous example, PPFF, we can test whether it's random or not. So next, this is hypothesis testing. So we have to be able to come up with a known and alternative hypothesis for the test. And HO will be the sequence of data is random. HA will be the sequence of data is not random. Then when N1 is less than or equal to 20 and N2 is less than or equal to 20, then the test statistics for the run test is G, and that will be the number of runs. Again, the test statistics is represented as G. If the sample size for both N1 and N2 are less or equal to 20, then G will be the number of runs. But if N1 is greater than 20 and also N2 is greater than 20, then the test statistics for the run test is given as following: G minus mu G over sigma G, or the standard deviation G. Where again, the mu G is given as 2 times N1 times N2 divided by N1 plus N2 plus 1. And also sigma G is given as square root of 2 times N1 times N2, parentheses 2 times N1 times N2 minus N1 minus N2, divided by N1 plus N2 all square and N1 plus N2 minus 1. This is if the sample again, N1 and N2 is greater than 20. So now let's state the steps. As usual, this is hypothesis testing. So first we need to state the claim, identify both the null and also the alternative hypothesis. We state the HO and HA. Now we specify the level of significance, example, alpha equal to 0.05 for the run test. Then we determine the number of data that have each characteristics and also the number of runs. So we have to determine the N1 and N2, and then the G. the G, either we can use the formula. So that's what is given here. If N1 is less than or equal to 20 and N2 is less than or equal to 20, then we use the table 12. Other than that, if N1 is greater than 20, N2 is greater, then we use table 4. Again, it depends on the textbook we are using based on our textbook. And that will give us the critical value. Then we calculate the test statistics. As we said earlier, if N1 is less than or equal to 20 and N2 also is less than or equal to 20, then we are going to use the G as the test statistics value. But if N1 is greater than 20 and also or N2 is great, again, here we should be careful with N and or. N1 is greater than 20 or N2 is greater than 20, then we use the formula Z equal to G minus mu G over sigma G. Then from there, we make our decision to either reject or fail to reject the null hypothesis. And it depends on the test statistics value and also the critical value. So here we say if G is less than or equal to the lower critical value, or if G is greater than or equal to the upper critical value, then we reject HO. Otherwise, we fail to reject HO. Then we do our interpretation or interpret the decision in the context of the original claim. So now let's see the example here. Here we say a foreman for a construction company records injuries reported by workers during his shift. The following sequence shows whether any injuries were reported during each month in a recent year. I represent a month in which at least one injury was reported, and N represents a month in which no injuries were reported. At alpha equal to 0.05, can you conclude that the occurrence of the injuries each month is not random? And this is the sequence given to us: I, then N, then I, then N, then I, then N. So we can able to find the number of runs and also the length. So first we state our HO and HA. The occurrence of injury is not random or is random. So our HO is random and HA is not random. Then this is our data set, and this will be 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for the whole year. So now we are going to represent I as N1 and N as N2. So the number of I's we have is 5. The number of N we have is 7. So in this case, we can say that our N1 and N2, they are less than or equal to 20. So we are going to use the G. So first, let's find the G. G will be the number of runs. So we can count here 1, 2, 3, 4, 5, 6. So we have 6 runs. The alpha is given to us as usual 0.05. Now here we say the critical value, because N1 is less than or equal to 20, N2 less than, we use the table 12. And this is how the table looks like. So in this case, we already know the value of N1, the value of N2. So we can see our critical value, the lower and upper limit. So it's 3 and 11. So now we know the critical value, we need to find the test statistics. So again, our G is 6, which is again the number of runs. Now here we say we fail to reject HO. We fail to reject HO. So again, J is YJ. YJ is 6. I think we all know the condition. The condition said if N1 and N2, they are less than or equal to 20, the test statistics value we use is G. Other than that, we have a formula to find G if it's greater than 20, if N1 or N2 is greater than 20. So now we know G is 6, and we can see that it fell within 3 and 11. Now, the condition tells us that if the G is either below the critical or above the upper, below the lower critical or above the upper critical, then again, we are going to reject HO. But G6 is within 3 and 11, so we're going to fail to reject HO. So here we see at a 5% level of significance, you do not have enough evidence to support the claim that the occurrence of injuries is not random. So it appears that the injuries reported by workers during the former shift occur randomly, because remember, HO, we state that occur random. HA not random. Okay, let's see another example here using the run test again. You want to determine whether the selection of recently hired employees in a large company is random with respect to gender. The genders of 36 recently hired employees are shown below. And also the alpha is given to us to be 0.05. Can you conclude that the selection is not random? So here again, we need to use the run test. So that's the etc. So here, first of all, we can state our HOHA. We can also find our alpha, which is given to us. We can find our N1, N2. We can say N1 should represent M, N2 should represent F, and we go from there, we find the G. So let's see. HO and HA, as usual, to be the selection of employees random. The selection of employees not random. Then based on the data set given to us, we were able to find all the runs MM, FFF, MM throughout. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the number of runs should be 11. But first of all, let's count how many M and Fs we have. So we have 1, 2, 3, 4, 5, 6. So the M's will be 6. Will be that's the number of runs. So the total run, let's see, the total run will be 11. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So now we find the number of F 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's 14. The M will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So that's 22. So again, here we have G again, for now, represent the number of runs, but that's not the test statistics yet. So we know our conditions said that. First of all, let's look here. So HO is random, not random. We know N1, we know N2, we know G, we also know alpha. Now we need to find a critical value, which is very straightforward here. Remember now, the N2 is greater than 20. So we are going to use table number 4. So based on the table number 4, we're able to find a critical value, 1.96 for both sides, 0.05. Then we can find the test status. So this time we have to use the formula since one of our N is greater than 20. So previously, again, if the N1 is 14, and let's say N1 is less than or equal to 20, N2 is less than or equal to 20, then G will be our test statistics. But if N1 is greater than 20 or N2 is greater than 20, so you don't have to be both. That's why previously we said we should be careful. Don't have to be. So in this case, we have to use the formula. So first we find the MG. We already have the value for N1 and N2, so we plug in the values. We get 18.11. Same thing to find the sigma G. We already have the value of N1 and N2, so we plug in all the values. That's the only two values we need to find both the mu G and the sigma G. And that gave us 2.81. Okay, so that's the case. We can find our Z, which will be G minus mu G over sigma G. G is given to us to be 11, and also mu G is 18.11, sigma G 2.81. So that gives us negative 2.53. So now let's look at our rejection region. So here we have negative 2.53 is outside. It's in the blue area. So here we are going to reject HO. So here we can say you have rejecting HO means not to. So here we say you have enough evidence at 5% of significant to support the claim that the selection of employees with respect to gender is not random, because HO said random. So rejecting HO means not random. So that will be the conclusion of this lecture. Again, this lecture will learn how to use the run test to determine whether a data set is random or not. In the process, again, we learn some few concepts. What is a run? How do we find the run? And also, how do we find the length of the run? And how do we do hypothesis testing with the run test? So again, wish everybody the best. Thank you.